That's Guillermo. So yeah, as Guillermo was saying, this is basically the work I have done in the first year of my PhD. And it's about reasoning with many valued interval temporal logics, which is a joint work with Guillermo, but also Carlos Nogueira, my supervisor, Pivi Doshovico, and Edward San. So let's begin. And I wanted to start with giving some motivation. And I want to start from an application example. Let's suppose that we are in a medical setting, and we have, for example, to model some patient exhibiting some symptoms of like depressed mood and insomnia. And those kind of symptoms can, of course, vary in intensity over time, and they can also like meet during certain intervals. And so we like a way to model both degrees of symptom severity and the temporal relationship between those symptoms. In fact, the real-world scenarios involve various degrees of truth, involve uncertainty, and involve temporal information. And we need to find a proper way to model this in our systems. And classical logic is insufficient for modeling such complexities because it only has true or false values, so it only has binary truth values. And therefore, we cannot represent partial truth for degrees of certainty, and they are not suited for representing temporal information, such as relations between time intervals. To solve the first one of those problems, we may involve many varied logics, so extending beyond the binary truth values of classical logic. And some examples are, of course, fuzzy logics. So if we take a total order between our truth values, and we consider, for example, the real values between 0 and 1, then we can define the classical Lukashevich, Gödel, or product logic. But if you don't want to involve a total order and we want something more general, like a partial order, we can involve, for example, a infinitely valued semantic for intuitionist logic. On the other hand, what we want to do is to model temporal relationship between events, and to do so, we can use interval temporal logics. Basically, they focuses on reasoning over time intervals instead than relation between points during over time. And for example, we can take Allen's interval relations, which basically model relations such as one interval is happening after one another, or it begins exactly when the other one begins, and so on. So what we what we propose is some notion of many value interval temporal logic, basically with the objective of modeling graded truths over time intervals. The challenges, of course, are integrating many value truth with temporal relations, but also developing reasoning systems to handle such complexities. And to do so, we propose a sound and complete tableau system for this kind of logic. We treated many valuedness using finite FLEW algebras. And we also provide an open source implementation for real-world applicability. So everything I will talk about today, you can find it open source on GitHub, and you can try it out yourself. So let's begin. Let's begin introducing interval temporal logic. And we are using Halper and Schoen interval temporal logic, which, of course, allows us to reason about time intervals using Allen's interval relations. And it's widely used in temporal reasoning, representation, and planning within AI. In table 1, we can find Allen's interval relations. So basically, what we need to define is usually a linear order between points. And we define the value for this relation, interpreting the equality or the less than between those points. And for example, we can say that one interval is happening after one other if the second point of the first interval is exactly the first point of the second interval. Of course, the limitation of classical HS is that it is based on binary logic. So we can only say if one interval is after the other. But what happens if those intervals are slightly apart? If those 2 points are actually very similar, but they not exactly coincide, we will say that it is false that one is after the other. So we would like to handle this kind of graded truth, we could say. We would like to say those 2 intervals are more one after the other, than some other two intervals, for example. And to do so, as I said, we introduced the notion of FLW algebras. FLW algebras are basically bounded commutative residuated lattices. We have a bounded complete lattice with upper bound 1 L over 1, 0, and a correspondent lattice order set. But we also have a commutative monoid that we refer to as T-norm. And also, since the resolution property must hold, we introduce the implication as the sup between all gammas, such that the T-norm between alpha and gamma is less than beta. Moreover, we define a T-conorm as having the dual operation with respect to the T-norm, and both these operations are monotone with respect to our partial order. We also say that this algebra is a chain if the order is total. So we find ourselves, for example, we can find ourselves in the fuzzy logic domain. And moreover, we say that those are standard if the values that we are considering are a subset of the real values between 0 and 1. And we say that it is finite if the domain is finite. In our implementation and in our Tableau system, we focus on finite FLW algebras. So basically, the implication of this is that, FLW algebras encompass several known many-valued algebras, such Gödel algebras and Wu algebras, which are the algebraic counterparts of Gödel logic and Lukasiewicz logic. They could also be a framework to work with product algebras, but of course, we lose those only using finite domains. But we can also use 18 algebras, so having a partial order. And in figure 2, we can find a partial taxonomy of those many-valued algebra. We can see that FLW algebras are a good framework to model this kind of many-valued logics based on this kind of algebras. Here's a simple example on how we can define a simple logic with only 3 values using a Gödel logic. So we interpret the T-norm and T-conorm as the minimum and the maximum between two values. And we define the implication as 1 if A is less than B or B otherwise, with the order in figure 3. And with those kind of many-valued logic, we can introduce a many-valued generalization of Alvarez-Shom logic. Basically, let's introduce syntax before. We have some propositional letters, P, Q, R, and so on. We have truth constants, alpha, in the domain, representing the elements of the domain of our FLW algebra. We have our usual logical binary connectives, conjunction, disjunction, and implication, but not negation. And we interpret unary modalities in the following way. For each relation, for each Allen relation X, we interpret the diamond as there exists an interval related by X where the formula phi holds. While we interpret the box as for all intervals related by X, phi must hold. And formulas are built inductively using those elements. Now we have to define a generalization of our linear order. So we define a many-valued linear order, in which basically having a domain D, we define 2 function mappings, one for the equality and one for the ordering, that basically must satisfy these 7 axioms. And this way, we also interpret many-valued strict intervals as all those tuples of points for which the mapping of the less tilde operator for points x and y is greater than 0. So, taking Allen's interval relations, what we have done is basically substituting equality and less than with the tilde equality and the tilde less than, and we get this interpretation of many-valued Allen's interval relations, in which we can see, for example, focusing on the first relation, the after again. If here I had that y and w must coincide, now they can be slightly apart. And the truth value for this relation, for this accessibility relation, won't be exactly 1, but it won't either be 0. It would be something like 0.9. Following with the semantics, we interpret a many-value interval model M as a tuple of many-valued strict intervals and evaluation function that assign true values from A to formulas at intervals. And we basically interpret logical connectives using the T-norm for the conjunction, the T-norm for the disjunction, and the implication that we introduced for the algebra for the implication. And we interpret the modalities in the way that we have in the equation. For example, for diamond, we basically evaluate the T-norm between the value for the accessibility relation and the evaluation of the formula at the interval we are accessing to. And we take the join, so the lattice join for all this evaluation for each interval that I have in my set of strict many-valued intervals. We also relax our interpretation of satisfiability and validity problems, basically stating that a formula is alpha satisfied at an interval if and only if the evaluation for the formula at that interval is greater than alpha. So we say that a formula is alpha satisfiable if for whichever interval such a model exists. We say that it is alpha valid if it is alpha satisfiable at every interval in every many-valued interval model, and it is valid if and only if it is one valid. But let's get back to our example. So now that we have introduced all this formalism, we can see how we can interpret a real problem with this kind of framework. So we had our patient with which exhibits symptoms of depressed mood that we assigned to a proportional variable P, and a symptom of insomnia for another variable Q. So symptoms, as we said, may vary in intensity over time intervals, and we can, for example, take an algebra domain A of real values between 0 and 1, a subset of the real values between 0 and 1. And for example, we can interpret a T-norm as the minimum between those values, such as in the Gödel logics. And our goal is to determine the degree to which an interval of depressed mood meets a period of insomnia. And we can write this as the following formula. So P, and after the interval I'm evaluating P, Q. So, for example, we say that P has value for the interval xy 0.7, and Q has value for the interval wz 0.8, and the accessibility relation between xy and wz is 0.9. So they are slightly apart, as in the figure 4. If we evaluate this, if we consider as the T-norm the minimum, we get the value 0.7. And so we can interpret this as it is not always the case that the period of depressed mood is followed by the period of insomnia. But we can say that this happens in a non-negligible manner. So we may take this into consideration in a medic would be interested in taking this into consideration. Okay, so now that we have introduced MVHS logics, we may want to find a way to reason about those kind of logics. And what we did was basically developing this fitting style tableau system for MVHS over finite FLW algebras to solve the alpha satisfiability and alpha validity problem, and also ensuring that this tableau is, of course, sound and complete. The tableau has a structure as in figure 5, so it is a tree-like structure in which each node is associated with a decoration of these two types, where we have a truth judgment, either it is true or false that we have that beta is less than psi or psi is less than beta, where beta is a true value from our FEW algebra, and psi is a formula. Then we also have an interval in which we are evaluating this judgment on this beta is less than psi or vice versa. But we also have a many-valued linear order associated with each branch of our tableau system. The purpose is, of course, to systematically explore possible evaluation to determine alpha satisfiability and alpha validity. And we do this starting our tableau system with, it is true that alpha is less than phi to solve satisfiability, or vice versa, starting from it is false that alpha is less than phi for proving validity. And then what we do is systematically apply some expansion rules to generate new nodes, or applying close rules to close our branches in case we find a contradiction. And the tableau always terminates, and it terminates if all branches are closed and we started from a set tableau, then the formula is not alpha satisfiable because I didn't find a model satisfying my problem. Or respectively, if I started from it is false that alpha is less than phi, that it is alpha valid because I didn't find a counterexample. Vice versa, if a branch cannot be closed nor further expanded, then my formula was alpha satisfiable because I found a model. Vice versa, it was not alpha valid because I did find a counterexample. Here are the tableau rules. Of course, I won't stop over them, but they are in the presentation. And in figure 14, we have an example with a very simple formula. So we have that at some interval, we can access with the relation after another interval in which P, and in all interval after our interval, P implies false. And we are, for example, considering this problem for one validity for the Gödel algebra with 3 elements. Sorry, we are considering validity here, one validity, one satisfiability. And so, of course, this formula cannot have a satisfiable model, and therefore it is not alpha valid, and all branches close. Maybe I can. Yeah, basically, this tableau system is both sound and complete, and it has been developed using the programming language Julia, chosen for its performance in numerical computations. And you can find it as part of an open source framework, namely Solid.gl, which is a package for reasoning, learning from structured and structured data. Specifically, you can find those tableau systems in the package releases.gl, and you can find a way to define your FUW algebras in the submodule many-varied logics from the solidlogics.gl package. Here, there's a code example just to show that in less than 30 lines, you can both define your algebra and ask the tableau system to solve your satisfiability problem. Here, there's another example with an 18 algebra with 4 values in which alpha and beta are non-comparable. And yeah, of course, since we have computational complexity that increases with both size of the algebra and complexity of the formula, we have to introduce some optimization techniques, which I won't go any deeper today because of time constraints. And we also did some experiment on this tableau system with some representative algebras, the one you can find in this figure, over 500 random formulas with it's up to 5, so up to 32 symbols, choosing a random alpha and keeping branch priority, since we are using also some search techniques to optimize our research of which nodes to expand, keeping it random for this, just for this experiment. And here are some results with a time out of 30 seconds. So yeah, just spending just a couple of words on the future work from where we want to go to in this second year of this research. We want to also give support for interval spatial logics. And we also want to start supporting the pointwise version of this logic, for example, LTL or some notion of cardinal logic. And fun fact, today in Bozen in Italy, we are also presenting another paper using those kind of logics, but applying them to a machine learning algorithm to extract many expert decision trees. So we can find a direct application of what I have shown you today. And thank you very much for the attention.